reason, I believe, is because they haven't figured out what absolute value inequalities mean. So let's go back to our definition of absolute value. Absolute value was the distance from zero. If you can remember that, then an absolute value inequality makes a great deal of sense. Let's take a look at an absolute value inequality at the board here. We go ahead and erase our number line. And again, if you feel the need to use that number line, rewind the tape, go back to it, look at it again. And the problem we're going to look at is 2x minus 3 is greater than 7. Certainly makes a difference whether it's less than or greater than. Now, before we go to our solution, I want you to look at this and see what it means. Think about what this says. What this says to me is that I have some number. Remember, 2x minus 3 is a number. We just don't know what x is, and therefore we do not know what 2x minus 3 is. This number is absolute value greater than 7. What does that mean? Well, let's assume this number was a positive number. That is, it's on the right side of 0. It's the distance away from 0, this number is greater than 7 units. Well, to be a positive number and be further away than 7, one must be to the right of 7. It's all the numbers out here, 7.1, 8, 10, 12, 400,000. But what if 2x minus 3 was negative? If it was negative, well, that would mean we have a negative number that's further away from 0 than 7 is. Well, negative 7 is 7 away from 0, and this number has to be further away, so it has to be beyond negative 7. So we can really see we have two solutions. We're back to a compound inequality. 2x minus 3 is either greater than 7, out here, or 2x minus 3 is less than negative 7, out here. The word or. One way I try to get my students to remember this is think of the absolute value symbol as two walls. Greater than means you're outside the walls. You're either outside up here or outside down there. It's an or situation. You think about it, you can't be both places. I mean, a person couldn't be on this side of the wall and on that side of that wall at the same time. It's impossible. So therefore, it's an or situation. You're either here or you're there. Remembering that, we can look at the visual. Because in the visual, what we have is the solution. Again, recognizing what the inequality means, we write the compound inequality. 2x minus 3 is greater than 7, or 2x minus 3 is less than negative 7. We solve independently the two inequalities, leaving the word or in between, and come up with x is greater than 5, or x is less than negative 2. And again, we check by picking numbers that were greater than 5, a number less than negative 2, and then finding a number that was not. For example, how about the 0? 0 is not greater than 5, 0 is not less than negative 2, and 0 should not work. Again, the difference between solving equations, we check the answers, and solving inequalities, we check numbers that should work and numbers that should not work. Let's take a look at the next inequality, which is the next visual. What is the difference between this inequality and the previous one? There are two differences. One is it's less than, as opposed to greater than, and it's less than or equal to. Now, what does that mean? Again, this means that the 5x minus 10 is closer to 0 than 15, or is the same distance. And I like to look at it, going back to my walls, that if you're less than, if your absolute value is less than, it means you're inside the walls. In fact, let's go to the board and take a look at what that inequality would look like, and then we'll go back to the visual to take a look at the solution again. 5x minus 10, absolute value, is less than or equal to 15. Again, the way I look at that is you are closer than the walls, which means you've got to be inside the walls. That is, you've got to be less than inside this wall and greater than inside this wall. So we're going to wind up with an in-between solution, like we had in a previous compound inequality. We should wind up with an answer that something is less than x or less than or equal to x, which is less than or equal to another number. So let's go back to the visual that gives us the solution to this inequality. Again, we write the word and because you must be both inside one wall and inside the other wall. What do we see? We solve the inequalities. We wind up with x is less than 5 and x is greater than negative 1. We have to ask ourselves the question, can you find a number that is less than or equal to 5 and greater than or equal to negative 1? And the answer is, of course, you can. Negative 1 is greater than or equal to negative 1 and less than 5. 0, 1, 2, 3, 4, up to 5. So all the numbers from negative 1 through 5, including negative 1 and 5. And again, the negative 1 and 5 are included because of the equals, less than or equals in the original problem. What do we have? We have our solution. Negative 1 is less than or equal to x, which is less than or equal to 5. Remember what I said. When you read one of these from left to right, it should flow. Negative 1 is less than or equal to 5. And x is between those two numbers. So again, in our checking, we could check 0, certainly is an interval. We could check a number that would not work. Think of a number that would not work. Hopefully you thought of a number like 6 or 7, which of course is not less than or equal to 5, or perhaps a number like negative 2 or negative 3, which is not greater than or equal to negative 1. And it should check. And again, I'll leave that checking up to you. You could stop the tape if you like and go ahead and check. Or we can go on to look at an alternate method. That is another method of solving these inequalities. As I think I've mentioned before, I don't believe that there's only one right way of doing something. And if you don't like this method with the walls, let me show you another method. So let's go to the next visual, which shows us an inequality. 3x plus 7 less than negative 5x minus 9. And it has the words, solve equation. What does that mean? It means simply change the inequality into an equation, which I've done. 3x plus 7 equals negative 5x minus 9. We know how to solve this. The steps, we get x equals negative 2. Now what does that mean? It means that when x equals negative 2, the equation has a solution. But we want a situation where one side is less than, not equal to the other side. So all we do is then we test points. So let's look at the next visual, which has our inequality. 3x plus 7 is less than negative 5x minus 9. And the words test points. Test points on the number line. For example, x equals negative 3. Well, negative 3 is less than negative 2. So if negative 3 works, that would mean that x would be less than negative 2. And we plug in negative 3 and we get that negative 2 is less than 6. The check mark indicates that negative 3 works, which means certainly any number to the left of negative 2, less than negative 2, should work. And we try a number on the other side. We try negative 1, because negative 1, of course, is greater than negative 2. This would test the solution x is greater than negative 2. You may say, why don't we just stop since we know x is less than negative 2? Oh, no. It's a good idea to check both sides to make sure you didn't mess up in your first part. And we plug in negative 1 into the inequality, and we get 4 is less than negative 4. This is not correct. This is not an answer. 4 is not less than negative 4. And therefore, if we go back to the next visual, we can see the original inequality. And it says, and this is important to remember, negative 3 worked and negative 1 did not. And again, our key thing was we had to work around the solution to the equation x equals negative 2. And therefore, x is less than negative 2 is the solution. I'll be quite frank with you. I like the first method better. But I have seen teachers who like to use the equation and then test points situation. And if that makes sense to you, or if that's what your teacher is using, there's a good example. But I'd like to go back now and review what we've done in this lesson. Because to me, solving inequalities again is very, very important. It really comes important in applications in later mathematics and even including in business courses and science courses, where you're dealing with the real world, where you have up to and including, or up to but not including, but certainly not beyond some things. For example, if any of you are applying to get into a military academy, the military academies have height requirements. They're different for males and females. And it's in between. You must be taller than a certain minimum height and shorter than a maximal height. And some people might ask how David Robinson ever got into the Naval Academy. That's because he grew a number of inches while he was in the Naval Academy. Had he been as tall when he applied as he is now, he would never have been admitted, because his height right now is taller than the maximal height of the inequality that's established for entrance into the U.S. Naval Academy. The first thing to remember is that solving an inequality is no different than solving an equation, with one exception. And that one exception is that when you multiply or divide both sides of the inequality by a negative, you change the direction of inequality. Less than becomes greater than becomes less than or equal to becomes greater than or equal to, etc. And the reason for this, if you've forgotten, rewind the tape. I think I've explained it fairly clearly. Otherwise, we simply solve as we did before. We isolate the variable, divide to get rid of multiplication. But remember, if you divide by a negative, you've got to change the direction of inequality. And then, instead of checking by looking at one solution or two solutions, as we saw in some equations, we test values. Values that should work, values that should not work in the original inequality. And the graphing of inequalities is important, because in equations, we have only one solution, x equals 7. Here, if we have x is less than 3, visualizing it is very helpful. So it's all the numbers to the left of 3, and we use the graphing techniques of using the number line. The open circle, the non-colored in circle, meaning less than or equal to or greater than or equal to. That is not including that number. The colored in circle means including that number. If a solution is greater than, for example, x is greater than 5, we'd have a circle, an open circle around 5, and a line with an arrow going to the right, indicating greater than. To the left, we have a line with an arrow indicating less than. This ends our solving linear inequalities, and we go on in the next lesson to looking at the line and the use of the line in correlation of real-world events.